This is 6.2.4. We now talk about orthonormal sets and orthogonal matrices. Orthonormal sets are orthogonal sets that have one extra condition, that the vectors are normal, as in unit vectors. Previously, we only had orthogonal sets of vectors, and now we want to make the vectors in this orthogonal set with unit length. That is, the norm of u1, the norm of u2, and so on up to norm of up are unit length. If that is true, instead of calling this an orthogonal set, they have a more special name, orthonormal set. If we use this orthonormal set to use it to span a subspace, or a subspace spanned by this set, then we call this orthonormal set the orthonormal basis for the subspace W. The simplest orthonormal set is what we have dealt with every day, which was, for example, 1, 0, 0, 0, 1, 0, 0, 0, 1 for the R3. But we are not restricted to having such simple standard basis. Any orthogonal set V1, V2, V3 they have length 1, therefore they become now orthonormal. Are also an orthogonal or orthonormal basis. That is, the V1, V2, V3 are not sitting on the axis, and they actually have values on x, y, and z direction. But nevertheless, V1, V2, V3 are orthogonal to each other. This example gives you V1, V2, V3, and we want to compute that they are really orthogonal to each other. And by that, all we need to do is to compute the dot product between all pairs v1.v2, v1.v3, v2.v3. The result shows that first they are orthogonal, then now we need to show that they are orthonormal. Then we basically compute the norm, and here is actually computing the norm square. Because the norm square is equals to 1, therefore the norm is also equals to 1, since v1 is equals to square root of 1 is equals to 1. Thus, in this example, we have just shown that first, v1, v2, v3 are orthogonal, they are unit vectors, and hence they form the orthonormal set. Because they are orthonormal set or orthogonal set, they are also linearly independent. And because they are linearly independent, they form a basis for R3. Note that they form a basis for R3 and not a subspace of R3, because we have 3 vectors for R3. Now, a quicker way to find whether the matrix U has orthonormal column is simply to perform the matrix multiplication U transpose U. And if this U transpose U gives you the identity matrix, then U has orthonormal columns. Let us think through this. U is a m by n matrix. U transpose is a n by m matrix. Therefore, I, if it arises, will be a n by n identity matrix. First, note that the length or the number m must be greater or equals to n. Otherwise, we'll never find orthogonal columns. Let us expand U transpose U using the columns U1, U2, U3. This is U represented in U1, U2, U3 columns. The transpose of U is U1 transpose, meaning that the column has now been made into a row. Column 2 is made into a row and column 3 is made into a row. We carry out the matrix to matrix multiplication and we study each of these elements in the final matrix. Because we only have 3 columns, our U transpose U would be only 3 by 3. Each entry of this 3 by 3 matrix is the dot product between Ui and Uj for all combinations of I and j. For example, in the top left hand corner is U1 transpose U1, U1 dotting with U1. The second element on the top is U1 transpose U2, basically is U1 dot U2. And the third one is U1 dotting with U3. And we carry on with the second row and the third row. Remember that we are interested to know if these columns are orthogonal. Therefore, Ui dotting with Uj when I is not equal to j are these entries that I have just circled. Basically, is the entries that are off diagonal, and the diagonal I will now draw it in green. The diagonals give us the norm of Ui square for I equals to 1, 2, 3. The off diagonal gives us the ability to check if the vectors are orthogonal. So for explanation, please read this text. Previously, we have discussed what is the orthogonal columns or a set of orthogonal column vectors. Now we want to define what is an orthogonal matrix. And an orthogonal matrix has a bigger idea. A matrix is called orthogonal only when the matrix Q being multiplied by its transpose on the left, so it's Q transpose Q gives you the identity. What it means is that the columns of Q and Q transpose must be orthogonal to each other, and the columns that are dotting with each other has length unit 1. So here, the word orthogonal here for orthogonal matrix not only requires the columns to be orthogonal, they requires the set of columns to be orthonormal. Now in the first example, we didn't require the matrix Q to be a square matrix. It can be a m by n matrix. Now if we are given a square matrix, that means we have n columns and n rows, and then Q transpose Q is still the identity. This is a very nice property. It means that Q transpose is equals to the inverse of Q. If such a matrix exists, it basically says that we are getting the inverse for free. Remember that trying to get an inverse of a matrix is an expensive operation, and if ever we have a matrix that its inverse is equals to its transpose, then we have a very nice property, and this is the property of the orthogonal matrix. You can also show that if Q is an orthogonal matrix, its transpose is also an orthogonal matrix. Now, orthogonal matrix has very nice property. If U is an orthogonal matrix m by n, and m by n is multiplied with a vector that is Rn, basically U of x can be viewed as a transformation of x using U. What is surprising is this result. The norm of u is equals to the norm of ux. For example, if y is equals to ux, the norm of y is equals to the norm of x when U is an orthogonal matrix. So this property has many interesting applications, especially in computer graphics. The second property of an orthogonal matrix is this. Ux dotting with uy is equivalent to x dotting with y. It says that when you perform dot product between x and y, and you perform dot product of transform x and y using u, the answer is the same. The dot product values is unchanged. And the last one is when x dot y is 0, then ux dot uy is also 0. Basically, I repeat, the use of u performing a transformation on x, so we can think of u operating on x giving us y. The y that has been resultant preserves the length and orthogonality of the vector x. I leave you to do this example by yourself, first showing that U is an orthogonal matrix by doing UTU to give you the identity. Second, we verify the property that the norm of x is the same as using U to transform x, but taking its norm, they are still the same value. This concludes our discussion for 6.2.4.